Okay, back in chapter 4, we looked at different types of chemical reactions. And synthesis reactions, did they absorb energy or did they release energy? Okay. How about decomposition? Neutralization? And then combustion? Perfect. So there are different sources of energy. We use things like natural gas and wood, coal, or gasoline. And most of the energy is stored as chemical potential energy, and we convert that energy into heat. Bless you. The amount of stored chemical potential energy that's available depends upon a couple of things. It depends upon what's the position of the electrons relative to the protons in it. What is that substance made of? Like, does it have a lot of carbon-carbon or carbon-hydrogen bonds, for instance, that may contain a lot of energy? But basically, anytime we're talking about chemical energy that we convert into heat, we're talking about enthalpy, right? And we've talked about this briefly before. So enthalpy is the change in energy available as heat. We call it delta H. What chapter did we review this in? What would you say? Do you remember? 4? Okay. All right. So everything that I'm discussing here is review. Do I need to do it again, or do we remember it? Do we remember it? Yes? Okay. So remember that enthalpy could be positive or negative. It's negative if it's exothermic. It's positive if it's endothermic. And the chemical energy or potential energy is known as bond energy. And if you take a look at the next page, remember, if we break a bond, it takes energy to make that happen, which means if we form a bond, it's going to release energy. And the balance between absorbing and releasing energy determines whether we're looking at an endothermic or exothermic reaction, okay? There are 2 ways to express the delta H value. Remember, we had thermochemical equations, which had the delta H value as part of the equation. And then we also had delta H notation, where it listed the delta H value after the balanced chemical equation, okay? Okay, let's turn to the next page, and let's talk about something new. When you're converting reactants into products, there's sort of this intermediate known as the activated complex, okay? And the activated complex is where you break bonds in the reactants and you form bonds in the products. It's this temporary, really high energy state, or the atoms for the reactants and products are involved. Let me give you an example. Here I have a reaction where hydrogen combines with iodine to produce hydrogen iodide gas. Right here, we've got the activated complex, okay? So here we are breaking the bonds in the reactants, which would be my H bonds. So these bonds are breaking, and then my II bonds are breaking, and then I'm forming bonds simultaneously between the products, HI. Okay, so this complex lasts like just for an instant, okay? And it's really unstable, and it decomposes immediately into the products, which are considered to be more stable, and the products would have less energy. So when the bonds are breaking, we're converting kinetic energy into potential energy, and then as the bonds are forming, we are converting potential energy into kinetic energy, okay? Now let's see what this looks like on a graph. In a previous section, when we talked about an enthalpy change, we gave you guys a sort of generic overview of what an endothermic and an exothermic process looked like. There's a little bit more detail involved, and that's what we're going to take a look at now. So let's come down here, and let's look at a potential energy diagram. Potential energy diagrams represent the energy changes that take place during a chemical reaction. Okay, so here you're going to notice that you've got potential energy on the y-axis, the reaction pathway on the x-axis, The x-axis will never be time. And then you have this curve where the reactants are on the left and the products are on the right. Notice the reactants have more potential energy than the products. This type of a curve is an exothermic process curve. They all look very similar to this, okay? What you need to know is, how do you determine the potential energy of different things using this curve? Where are the reactants? You can also write the reactants in here. This is actually my hydrogen and my iodine from the reaction up above. Sometimes you'll see them write the chemical formulas here. And then if you want the actual value for the potential energy of the reactants, you would look here on the y-axis. So let's say that this is 20 and this is 50. So the reactants have 50 kilojoules per mole for their potential energy. Your products, which are down here, which are your 2HI, okay, they're at 20 kilojoules per mole. A couple of other things that you definitely need to know will be the activation energy. Activation energy is abbreviated as a capital E, lowercase a. You will sometimes see it written as a capital E with a lowercase ACT. It means the exact same thing. The activation energy is between where the reactants began and the highest point on that curve. Okay, so let's say that this value up here was something like 90. This activation energy would be 90 minus 50, so it would be 40 kilojoules per mole. Okay, so I would expect you to be able to come up with that. Another thing that you should know is, what is the potential energy of the activated complex? So the activated complex is at the peak. Okay, so this potential energy for the activated complex would have to be 90 kilojoules per mole. Something else you need to know is how to calculate the enthalpy change, which they tend to call the heat of reaction. This is going to be the difference between the potential energy of the reactants and the potential energy of the products. Be careful when you calculate this. This delta H value will be calculated the same way every time. It will be the potential energy of the product minus the potential energy of the reactant. So that means in this case, this would be 20 minus 50, which is negative 30 kilojoules per mole. It makes sense that it's negative because this is an exothermic process. Now, you can read potential energy diagrams in the forward and the reverse direction because some processes are reversible. So the forward direction would be moving from left to right, the normal way that you would read things. The reverse direction would be going from right to left. So if you were going in the reverse direction, that means the reactants would be here and then the products would be here. You're not necessarily switching them. You're just going in the reverse direction saying, okay, 2HI would now be my reactant. H2 and I2 would now be my product, okay? Then you would be asked to determine things like, what's the activation energy of the reverse direction? That means it would be where the reactants are, which would be down here, and then wherever the peak is. So it would be 90 minus 20, which is 70, okay? So the reactants for the reverse would have 20 kilojoules per mole. The products for the reverse would have 50 kilojoules per mole, okay? Okay, this reverse curve would be an endothermic curve, because it's the opposite, right, of exo. Okay, let's go to the next page. Let's go to the reversible reactions. I want to go over here. Let's go to these practice problems, okay? All right. For A, I want to know if the forward reaction is exothermic or endothermic. You tell me. Yeah, this is endothermic, and the reason is because the potential energy of the product is greater than the potential energy of the reactant. Like, we are absorbing energy, okay? B, indicate the following values for the forward reaction. What's the activation energy?
30 kilojoules.
Tell me how you got that. You're right.
140, which is the peak, minus 110.
Yeah, so this would be 30 kilojoules per mole. And that's because wherever the reactants began to the highest point on that curve, that would be your activation energy. Okay? What would the enthalpy change, which is also known as the heat of reaction, be? Yeah, how'd you get that?
Between the reactants and product.
So 130 minus 110 is 20. So that means wherever the products are and wherever the reactants are, you're going to subtract this. So this is my delta H right here. All right, this is my reactants. And then this is my products. Okay. What's the potential energy of the product? 130. What's the potential energy of the activated complex?
140.
140. They may sometimes refer to the activated complex, which is here, up here at this peak. They may sometimes refer to that as the transition state. Okay, so the activated complex may be called the transition state depending upon what textbook you're reading, if you have a tutor, or what online resource you're looking at. Okay? Okay. Let's take a look at number 2. They want us to indicate what the measured values are, Roman numeral 1 through 4 on this potential energy diagram. Okay, so you could be referring to something that's reversible here. So for Roman numeral 1, what would you say that that is?
The forward activation energy.
Yes, this would be the activation energy of the forward reaction because it goes from the peak to where the reactants typically are. Okay, then you have Roman numeral 2. What would you say that is?
Reactants potential energy.
Yeah, this is the potential energy of the reactants. It could also be what? Potential energy of the products for the reverse, right? So this is potential energy reactants of the forward reaction, or the potential energy of the products for the reverse reaction. Okay, what's Roman numeral number 3?
Reverse activation energy.
Yes, this would be the activation energy of the reverse reaction. And then Roman numeral 4.
Enthalpy change.
Yeah. A couple things that you should highlight at the bottom of this page would be the activation energy is always smaller for an exothermic reaction. So isn't this forward reaction exothermic? So that means that this right here, this would be the activation energy of the forward reaction, which is exothermic. Do you see how small it is in comparison to the reverse reaction, which is endo? So that makes sense because it takes a lot more energy to get an endothermic reaction to go. Okay, let's take a look at the last page.